Okay, so we are going to discuss Cartesian vectors today. As you guys know, I kind of explained to you yesterday that these are kind of to translate our geometric concepts from our first vectors unit into how we can express vectors on a Cartesian plane. They're sometimes also called algebraic vectors. So what this helps us do is it just helps us do some different operations with vectors that we wouldn't necessarily be able to do if they were expressed geometrically. So you'll kind of see a bunch of different applications of these types of algebraic vectors. Okay, so our notation, like we said yesterday, was we always want to express our Cartesian vectors as if their tail is at the origin and their head ends at some point AB. And then we express the vector with square brackets. So this is kind of similar to, we have to kind of make the distinction here between this notation and our interval notation from advanced functions because it looks similar. But when we're talking about algebraic vectors, thank you, we will think of the square brackets as if they're just indicating this is an algebraic vector, not that it's inclusive from point A to point B. So it's just telling us that's where the tip of the vector lands after it starts at 0, 0. All right, so yesterday we practiced drawing a couple of vectors on our intro assignment. So the vector 4, -6, the tail of this vector would start at 0, 0, and then the tip of this vector would be ending at 4, -6. Oops. So this is how we would draw our vector. So this is our vector for -6. You don't necessarily have to label it, but I'm just labeling it for our purposes here. Okay, so I want to imagine that we maybe shift this vector somewhere else on this Cartesian plane. So we're going to imagine that perhaps we, Erica, can you give me a number that you want to shift up? 2, and Rachel, give me one that you want to shift left or right. Yeah, okay, so we'll shift up 2 and 3 right. So I'm going to take the tail and I'll shift it up 2 and 3 right. And it will become a point at 3, 2. And then I'm going to take the tip of this, I'm going to shift it up 2 and 3 right. And my tip will be at the point 7, -4. So my question is, how are the tip and tail of this vector, so the tail of this one we said was 3, 2, and the tip of this one was now 7, -4. How are these points related to the points 4, -6? If we look at 7 and 3 and -4 and 2, Ryan? Yeah, the vector itself is parallel to our original vector, so it should be actually parallel and equal to. Erica? Yeah, true. Is there a connection between how we could get to the endpoint and the point of the tip? How we could get to that? Sarah? Yep, so they will definitely move together if we shift them.
Like the difference between those 2 points is the number.
Yeah, so if you notice here, the difference between 7 and 3 is 4. And the difference between 4 and 2 is actually our -6. So if I call this one like my x1, y1, and my x2, y2, I can actually find where that tip of the vector would point, or it would end starting at 0, 0 if I do 7 - 3 and -4 - 2. And then I have my 4 and my -6. So that's kind of where our grounding in how we figure out if I have the tail and the tip of a vector, how I figure out that kind of formula to find the value of that vector when arranged from 0, 0 to the tip of the vector. So our general formula here is going to be, when we want to figure out a vector, we will do x of the tip minus x of the tail to get our new x coordinate for our vector. And then I will do y of the tip minus y of the tail. And essentially what this does is if I just have like 2 points and I want to create a vector from those points, a Cartesian vector, it gives me that Cartesian vector arranged from 0, 0, and the tip on whatever point it ends up falling on. Okay, so as an example for you here, I can plot the vector for sure going from -2, 3, so it would start here, and ending at 1, 7, so it just goes like this. Oops. Okay, but again, ideally, for these Cartesian vectors, we want to express them as if they start at 0, 0. So if I express it starting at 0, 0 and the tip ending somewhere else, it's going to be an equal and parallel vector. But it's just kind of like a common vector notation that we use for Cartesian vectors. So our tip here, this is going to be x of the tip and y of the tip. And this is going to be x of the tail and y of the tail. So if I want to actually figure out where this vector goes, I mean, I can definitely slide it down to 0, 0, and then I'll slide the tip down the same amount, but we can also calculate it as well. So I can do x of the tip minus x of the tail, and then y of the tip minus y of the tail, and I can find where my new vector should be positioned. So it should be positioned at 3, 4. So starting at 0, 0 and ending at 3, 4. And again, our vector should look like it's parallel and equal in magnitude to our black vector that I just showed you here. Okay, so that's how we can just calculate it algebraically.
I don't understand why we would need to know just to know where it started from, right?
Yeah, so we just try to express them all in terms of starting at 0, 0 and ending somewhere. So it will give us still a direction, and it will also give us like a magnitude of that vector. This isn't in vector notation, right? Like if it starts here and ends here, that's not really in vector notation. So when we want to put it in vector notation, that's what we have to do. Vanessa, do you mind shutting that back door for us? It's just a little noisy. Ryan? I mean, you can. You shouldn't have to, even plot this in order to figure out that 3, 4. But you can, yeah, so if I asked you to find it, you can show it starting at 0, 0 and ending at 3, 4. You don't have to even necessarily draw the black one. But if you want to draw it to check, you can. Because we can also check that if I shift this down 1, 2, 3 and over 2, the tail should be doing the same thing. So 1, 2, 3. And over 2. So that kind of tells me that my math is correct there. We shifted them the same amount. Okay, so we'll try a few more here. So if we want to find the vector from 3, -11 to, in other words, ending at 7, -1, this is going to be the x of the tail and the y of the tail. And this will be the x of the tip of the vector and the y of the tip. And then our vector is going to be equal to 7 minus 3 for the x-coordinate and -1 minus -11 for the y-coordinate. So we'll get the coordinate 4, 10. So again, we're assuming that this vector is starting at 0, 0 and then extending, and the tip ends at the point 4, 10. So far, so good? Okay, so here we're given 3 points. We want to find BA and AC. So remember, guys, when we express vectors in this notation, let's talk about BA. Which one's the tail and which one's the tip? B or A? B, yeah. Okay, so B is our tail, and A is our tip in this case. So when I'm finding BA, I want to think about B, when it's 3, 5, as x of the tail and y of the tail. And then I want to think about A, the x and y coordinates, as x of the tip and y of the tip when I'm calculating this. So vector BA is going to be equal to 2 minus 3 and 1 minus 5. So we'll get -1 and -4 for BA. Okay, When we calculate AC, things change because A is now the tail of this vector and C is actually the tip of this vector. So when I think about the point A, I want to think about this as like x of the tail and y of the tail. And then when I think about vector C, I want to think about that as x of the tip and y of the tip. So when we calculate vector AC, we're going to do -1 minus 2 and then 3 minus 1. So we'll get -3, 2. So far, so good? Not too bad? Essentially what we're doing, guys, is we're using almost like a distance formula where we find the difference between the x's and the difference between the y's in order to see how many units we go over and how many units we go up or down. Any questions on these guys before we move forward? Okay. Unit vectors. So we talked about this a little bit yesterday as well. We have vector I, which is known as the unit vector or vector of length 1 in the x direction. And we have vector j, which is the unit vector or vector of length 1 in the y direction. So we did draw these on our graph yesterday, but we'll just redraw them again. So this is vector I. We also call this I hat. So it starts at 0, 0 and ends at the point 1, 0. And then j, or j hat, is our vector that starts at 0, 0 and ends at 0, 1. So we worked yesterday to express our Cartesian vectors in terms of our unit vectors I hat and j hat. And essentially what we do is we just kind of create a little sentence here that says like how many scalar multiples we want of I and how many scalar multiples we want of j in order to get us to that point. So how far do we go over, how far do we go down or up or whatever. So we're saying we want 4 scalar multiples of the unit vector I, so we're going in the direction 4 units on the x-axis, essentially, and then we're going down in the direction of the y. So scalar multiple of 4i, so 4 units, because I is 1 unit, and then down 6 units, because j is in the vertical direction by 1 unit. Okay, so this is kind of like a vector expression where we're showing the scalar multiples of I hat and j hat as like an addition or a subtraction of vectors. No, it should be just like a full expression like that. That was like a little typo on my solutions from yesterday. But yeah, it should be like an expression of their additions or subtractions depending on which direction you're going. Okay, so think of I as the x direction and think of j as the y direction. Okay, magnitude. So I'm just going to kind of formalize this for you guys yesterday. So the magnitude of a vector comes from our formula that we learned, I think, back in grade 10 when we found the distance between 2 points. So we're going to say if we have some vector, we'll call it u. Or actually, sorry, just regular u, not magnitude of u. That's coming in a second. We're going to say we can express this vector as an x-coordinate and a y-coordinate, just like I showed you guys above. So some distance over on the x and some distance up or down on the y. Now if I have this, this is saying that my first point or the tail of this vector is 0, 0, and the last point on this vector is ux and uy. So when we actually find distance, usually we do x2 minus x1 squared plus y2 minus y1 squared. But I don't need to do that in this case because I know that the tail of this is 0, 0. So what we end up doing in order to find the magnitude of our vector is we'll just take the square root of the x-coordinate squared, and we'll add that to the whole square root of the y coordinate squared. So, sorry, I said that kind of weird, but each coordinate squared and added, and then we take the square root of the whole thing. Okay, this is also essentially just from like Pythagorean theorem. Like if we think about separating our vector into like a right angled triangle and just finding the length of that vector, this is what we're doing. Okay, so that's going to be our formula. Okay, so adding vectors, this one's really straightforward. If I want to add A and B, all I need to do is add their x components and add their y components. Graphically, what I'm doing is I'm graphing vector A, so maybe we'll do that in red. So I'm graphing vector A, it goes from 0, 0 to 2, 3. And vector B goes from 0, 0 to negative 1, 5. Okay, so the only problem here is that when I want to add vectors, I don't want them arranged tail to tail. That's kind of a problem. So what I need to do is I kind of need to use that parallelogram method that we talked about, and I need to shift vector B so that it's starting at the tip of vector A. So how far would I have to shift this tail? Well, I have to go 1, 2, and then 1, 2, 3. So I'm going to do the same thing with the tip here. I'm going to go 1, 2, and then 1, 2, 3 to find out where that tip ends up here. Okay, so just counting the spaces. And this is where I want to express our vector B. Okay, the reason I want to do this is because I want to find out when I'm doing A plus vector B, I want to find out how they're arranged tip to tail, and then my resultant will actually be the vector that starts at 0, 0 and ends at the tip of vector B, right? This is our resultant when we do A plus B. So can somebody tell me what our resultant is based on where we see the tip of this landing? 1, 8, yeah. So we can kind of see that here. So we can also kind of just see if I'm adding the x components, I'm getting 1, and if I'm adding the y components here, I'm getting 8. So that should make sense both graphically and algebraically when we think about adding those vectors together. So algebraically, essentially, add your x components, add your y components, and you're done. So we would do our 2 plus negative 1, I think is what the points were. Yep, and then 3 plus 5, and we'd have our vector algebraically. Questions? Are we okay so far? So you guys can imagine if I were subtracting two vectors, could we kind of extend this idea here? What do you guys think I would do if I was subtracting vector A by vector B? Yeah, AX minus BX, AY minus BY. Yeah. So smart, so smart. Okay, vector times scalars. If we multiply vector u by k, we will get k times vector u, and that says that I'm going to take my actual Cartesian vector here and I'm going to multiply it by a scalar multiple of k. And what actually ends up happening here is I can actually multiply each individual component of this vector by the scalar multiple k. So I'm stretching the x k units, and I'm also stretching the y k units. So this is actually equal to k times the x coordinate of vector u and k times the y coordinate of vector 2, or vector u. Okay, so just an example for you guys here. If I want to find half of v, or vector v, I'm going to do a half times our Cartesian vector here. And essentially what I'm doing is I'm just distributing that half into my bracket here. So I'm going to do 1, negative 1 times a half, and then 3 over 5 times a half as well. And our half of vector v will become negative half and 3 over 10. So this is the vector that represents the vector v, but half the magnitude. So it's still parallel to v, but it's half of its magnitude. Okay, so graphically, we would be looking at essentially a vector. So if this is, I'm just kind of drawing a vector here, but if this is my vector v, let's say, then half of v is going to be the vector in the exact same direction, but it's just half the magnitude. So you can kind of see them there. So far, so good? Okay, we're almost done. So collinear. When two vectors are collinear, we are basically saying that they can be drawn on the same line, or that they lie on the same line. In other words, they have to be scalar multiples of one another. So they're parallel, but they don't necessarily have to be equal in magnitude. All right, so if vectors lie on the same line, or they are parallel, but not necessarily equal in magnitude, we say that they're scalar multiples of one another. The way that we can check if two vectors are collinear, or scalar multiples of one another, is we check the ratio between the x-coordinates of the vector, and we see if it's equal to the ratio between the y-coordinates of the vector. So essentially what we're going to do is if I want to check to see if vector u is collinear with vector v, then we will say the x-coordinate of the u divided by the x-coordinate of the v will be equal to the y-coordinate of the u divided by the y-coordinate of the v. What does this mean? I think visually we can usually see if vectors are scalar multiples of one another, but sometimes if they're like fraction scalar multiples of one another, it can be a little bit more difficult to see. So if I wrote the vectors like 2, 4 and 6, 12, are these scalar multiples of one another?
Yes.
Yeah. So if I multiply my first one by 3, then I get 6 and 12, right? So basically, this formula is telling me I'm going to check the ratio between the x's and see if it's equal to the ratio between the y's. And here, because 3 equals 3, these are scalar multiples of one another. So it gets a little bit more complex when there's like decimals, but if you do this kind of standard little check between the x's and the y's, you should be fine. Just be consistent with the one that you put on top and the one that you put on bottom on each side. Yeah, I could flip it too, and that would be fine, a good check. So let's say, guys, Vanessa. Now that's going to be on my video. People are going to be weirded out. Let's say that this is vector u, and we'll call this guy vector v. We're going to do a little check here. Again, you might be able to see with your eyes already if one of these is collinear with the other. But we'll do a little check. We'll do the x of the u divided by the x of the v, and we'll see if that's equal to the y of the u divided by the y of the v. Okay, so I'm going to do 3 divided by the x of the v, and then I'm going to do 5/6 divided by our y of the v, which is negative 5/12. Okay, so if you calculate this guy out on the left, you'll flip and multiply, the 3's will cancel, and you'll be left with negative 2. Again, flip and multiply, the 5's cancel, you have 12 divided by 6, and you get negative 2. You can also just sub it into your calculator, which is totally fine. So yes, they are collinear. What did you say is so shocking?
Like those numbers like over each other being divided, like I would never guess like in a million years that like I'm gonna negative 2.
That would be 2, yeah.
Like would you be shocked if like you didn't know? Like if you just saw that? Like would you guess?
Probably not. I don't know. I can imagine like flipping it in my head, but yeah, I get it.
6 and 12, so it's double.
Yeah, 6 and 12.
So what we can say to make a statement of these vectors being collinear is I can actually say that the vector 3 and negative 5/6. Hello. Okay, so can you guys tell me if I wanted to make a statement? Ryan and Anil, are you ready? Almost done. Stick with me. What? Oh, yeah, sorry, my mistake. Can someone tell me how I would make a statement about how these are collinear using a scalar multiple, now that we've found this negative 2? So vector 3, the vector that goes from 0, 0 to 3, 5, 6 is, how do the scalar multiples work here? Negative 1 over 2, or I can express this as a scalar multiple of negative 2, sorry,
negative 1 over 2 times the first one.
right, negative 1 over 2 here, or I can say that this is negative 2 times my other vector here, right? So I can say it two ways. I can say this vector, 3, 5, 6, is a scalar multiple of negative 2 times our other vector, or I can say our other vector, negative 3 over 2, negative 5/12, is equal to negative 1/2 of 3, 5/6. So either way, but I think this way is kind of a little easier. So you can also say this. This is also another option, which is completely acceptable. No, it's either the first one that I showed you or the second one. Those are the only two options. Okay? So if I do the u divided by the v, I'm finding the scalar multiple that I need to multiply the v by to get u when I do that. Or if I do the reciprocal of it, I'm finding the opposite. But when I put the u on top and I divide it by v, I'm finding that scalar multiple that I have to multiply the second vector by, vector v, to get u.
So all equivalent and opposite vectors are collinear, but not all collinear vectors are equivalent or opposite.
Correct.
Is that right?
Yes, correct. Yep.
So one more time.
Which part? So he said all equivalent and opposite vectors are collinear, but not all collinear vectors are equivalent and opposite. Because collinear vectors are just like parallel vectors, essentially. So if I have an equivalent vector, that's still parallel, so it's collinear, and opposite vectors are also like just a negative scalar multiple. So those are also collinear. Okay. Okay. Okay, last one. Do you guys have this on yours? Oh, yeah. Okay, good. Okay, converting geometric vectors to Cartesian vectors. The question in all of your minds, right? You were laying up awake last night thinking about this. How do I?
I did think about that.
Did you? That's good. Okay. So how do we convert vector u, if it's 500 meters? How do we convert vector u, if it's 500 meters at a degree of north, 10 degrees west, into our Cartesian vector? That is a really good skill to have, especially if we're doing any application type questions. Sorry, that is not needed. Yeah. You did it? Not cosine law, but SOHCAHTOA. Yeah. So, yeah, that's really good. So guys, we're going to make a scale, and we're going to try to plot our vector as accurately as possible. So may I suggest that we do 1 centimeter is equal to 100 meters here? And I want northwest, so I know that I'm going to be starting in the north and then moving toward the west 10 degrees. So I want to draw a vector here that's approximately 10 degrees from the north line, and it should be 5 centimeters long, whatever that looks like on your page. No, it's going to be in the gym. I know.
I like it.
Me too. Okay, so here's the deal, guys. If I want to figure out this vector starting at 0, 0, if I want to figure out where this tip would be, I need to know what is the x component of this vector and what is the y component of this vector. Agreed? I need to know like how far left we go and how far up we go to get to this vector. So I want to think about this as kind of like a right angle triangle where this is our x here and this is our y. Sorry, I got an extra line here. Oh, and again. One more time. Okay, so I'm going to show you guys a little short form, and then I'll explain to you why this exists. But essentially, if I want to find vector u, we are using kind of what we used with our forces when we separated into our perpendicular force components. We're going to have the magnitude of u times the cos of theta, and then to get our x-coordinate, and then the magnitude of u times the sine of theta. And our theta here,
Is 70.
right, so it's going to be, right, yeah, so it's going to be the angle between our vector and the closest x-axis. Just like we do in our trig when we're doing like a reference angle with cast rule. So our theta that we use must be the angle between your vector and the closest x-axis.
Mrs. Michaela, shouldn't it be negative because it's in the negative x? And 500 cos 80 is not negative?
So you have to decide based on cast rule whether your answer is negative or positive.
Okay.
Yeah. So this is just the general formula, and then again we have to consider what quadrant we're in as well. Okay, so I'm going to show you, well, let's just talk about y for a second here. I don't want anybody staying up late tonight thinking about this, so we might as well just talk about it. So y. Why does this end up equaling these magnitude of u times the cos theta and magnitude of u times sine theta? Okay, so I'm just going to show you. But beyond this, after I show you the calculations, we're just going to use this short form up above. That's our quick way to find the x and y components. But why? So if we think about the 80 degrees as our reference angle here, I know x is adjacent, y is opposite, and our 500 is hypotenuse. And that vector will always be our hypotenuse, right? Because we're separating it out into its x and y components. So if I want to find x, I need adjacent, but I have hypotenuse. So which trig ratio am I going to use in this right angle triangle? Cosine. So the cosine of 80 is going to be equal to x adjacent over the magnitude of our vector, which happens to be the hypotenuse, which is 500. And then when I isolate for x here, I'm doing the hypotenuse, or the magnitude of my vector, times the cos of 80. And that gets x by itself. So this right here, this expression that we just found, is actually the magnitude of our vector u times the cos of theta. So rather than rearranging this every single time, we just use this general formula where the x-coordinate can be found using cosine and the magnitude of u, and the y-coordinate is found similarly as well. Yep, Sarah?
Couldn't we also use like the angle 10 and just like switch cosine and sine for like x and y? Like x would be like the sine.
Yes, you can, but if we're going to use the general formula and just do it like the same every time, that's the angle that we want. But yes, technically you can find it the other way as well by creating that other right angle. Ryan, yeah? Again, we don't need to do that because we have this general formula. I'm just showing you why this formula is true for now, but we're not going to be doing these calculations in the future. We're just going to be plugging into this formula up here. Yeah. If you want to, but again, you don't need to use sine law and cosine law when you have a right angle triangle, right? Yeah. So we don't want to do more work than we need to. Okay, so does everybody see why this formula is true here in terms of this question? So can you guys, for me, figure out our vector u if we sub it into our formula here, magnitude of u times the cos of the angle between our vector and the closest x-axis, and then magnitude of u times the sine of our angle between our vector and the closest x-axis?
Should we leave it as exact values?
I don't really think, like when you have 80, no, but if it's 60, 30, or 45, you could.
Okay.
Like if they're special angles. Okay, the other thing, guys, this is really important right here. Okay, last point. The other thing that we need to be aware of is we need to be aware of what quadrant we're in and where our x's are negative and where our y's are positive. So we want to decide on positive and negative based on the quadrant that we're in. So in our current quadrant, the upper left quadrant, if I'm going left on the x-axis, should my x be negative or positive? Negative, right? Because we're moving to the left of the x-axis, which means we're moving in the negative direction. Now, if we're in that upper left quadrant and I'm moving up on the y-axis, should I expect my y to be positive or negative? Positive, because we're moving up on the y-axis. Okay, so I know already here that this one's going to be negative, and then my y-coordinate will be positive. So can somebody tell me what we get for each of these coordinates? Let's say to the nearest hundredth, so 2 decimal places. Yep. Great, and then the second one? 0.4 exactly?
0.40.
Oh, okay, so we'll just say 0.4. That's good. Okay, so don't forget, guys, you need to know what quadrant you're in to decide whether that x and y coordinate are negative or positive. Okay, so this is an important part. Okay, any questions on this one? So, do I expect you to show me all of this work every single time?
No.
No. All I expect you to do is just sub right in here, and then you'll find the magnitude of your x component and your y component. Okay? Good? All right.